Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is resistance. Our objective is to introduce the basic electrical quantity of resistance. We'll examine properties that influence resistance and learn how to calculate resistance. Additionally, we'll take a quick look at the American wire gauge. Spoiler alert, I'm going to show a video of glass conducting electricity at high voltage. If you want to see something cool, at least stick around for this. I know the enthusiastic among you are eager to dive straight into circuit analysis, but I want to cover a couple basic topics in detail, resistance among them, before we reach this level. St. George didn't start out slaying dragons. He started off killing newts, killing lizards, and worked his way up to killing crocodiles before he even thought about challenging a dragon. This stepped approach serves a couple purposes. 1. I don't want you to pull a muscle. This might be the first time some of you have ever tackled a technical course before, and it will serve us well to perform some low-intensity reps of basic math before we dive straight into battle. Fair warning, we're going to be doing some calculations, unit conversion, and algebraic manipulation during this lecture. The level of difficulty for these procedures should serve as an indicator of how things are going to go for the remainder of this series. If you feel confident in performing these tasks with no outside assistance, you're tracking. If not, you are not tracking, and you need to get tracking ASAP. 2. A discussion of resistance leads us right into discussion of basic electrical components and instrumentation, among them resistors and the ohm meter function of the digital multimeter, or DMM. The next couple lectures about resistance will prepare us to examine the ohm meter function and use it to measure the resistance of various configurations of resistors. Finally, and most importantly, a discussion of resistance is vitally important. Recall from our previous discussion of basic electrical properties that resistance is opposition to current flow. Without resistance, current would be uncontrolled and potentially dangerous. Wrapping back to our first reason why we're discussing the property of resistance, a review of basic math skills, you'll realize the properties that influence resistance make perfect sense. It's extremely satisfying to realize that the numbers and relationships we'll examine have some meaning and application to the real-world desire to control current flow. Recall that resistance is measured using the unit ohm, symbolized by a funny-looking horseshoe thing called the ohm. Actually, it's the Greek letter omega, but everyone calls it ohm. More ohms, more resistance, more opposition yields less current. Conversely, less ohms, less resistance, less opposition yields more current. If you have to represent unusually small or unusually large quantities of resistance, you can always use engineering prefixes to assist you. For example, 2,400 ohms is better represented as 2.4 kiloohms, and 0.003 ohms is better represented as 3 milliohms. Engineering prefixes just make these entries easier to read and write. Additionally, the levels of magnitude indicated by a transition from one prefix to the next clearly and quickly indicate whether some quantity is larger or much larger than another. We'll start a discussion of resistance with the two obvious limits, something with infinite ohms of resistance and something with 0 ohms of resistance. Infinity is kind of a mathematical cop-out, but when I use the term infinite, realize I mean something with immeasurably large resistance. So large you can't measure it, so it may as well be infinite. These two extremes represent special case scenarios so important, we're going to give them their own identifying terms. A path or device with infinite ohms of resistance is called an open. A path or device with 0 ohms of resistance is called a short. An understanding of opens and shorts, and the important differences between them, is critical to your success as a technician. In fact, an understanding of these two scenarios is so important, I am confident enough to say that fully 90% of the problems and troubleshooting scenarios you may find yourself in the future are the result of an open. 9% of these problems are caused by shorts, and only 1% are caused by something else, most likely your lab partner. Opens and shorts need not necessarily be sources of problems. Inadvertent opens and shorts, yes, but think of a simple electromechanical device designed to control current flow by purposely making and breaking electrical connection, namely the switch. An open switch presents a path of infinite resistance through which no current can flow. A closed switch, in contrast, presents a path of 0 ohms of resistance through which current can flow. Consider a series or inline relationship of a DC source, a switch, and a light bulb acting as an electrical load modeled as a resistor. When the switch is open, there is no current flow because the resistance of the switch is extremely high. So high, in fact, that the resistance of this circuit is infinite. An open condition does not allow current flow. This would be the off position for the switch because the switch does not allow conventional current to flow from the positive terminal of our supply to the negative terminal through the electrical load. The space between the terminals of the open switch represent an impassable chasm to any charges that have incentive to move supplied by the source. Consider the opposite scenario, a closed switch. This would be the on position for the switch because it now represents an effectively 0 ohm resistance. In other words, a short. In this case, charges or current can now move or flow through the switch and by extension the electrical load. A closed switch conducts current with no opposition, i.e. 0 ohms of resistance. What is controlling or opposing charge movement in a circuit are those electrical load devices that precede or follow the switch. In this case, it would be the light bulb. If the light bulb wasn't there, we'd have a serious problem because there would be no opposition to current flow and it would flow in an uncontrollable fashion, i.e. extremely high and dangerous. Our light bulb, however, opposes or resists the cause of charge movement, i.e. the voltage differential across our source, and the effect, moving charges or flowing current, is controlled and manageable. This is what is known as a high-side switching arrangement, where a switch is positioned between the positive or high side of the source and the electrical load is illustrated. This is probably the most common switching arrangement you'll see because it's the safest. Alternatively, one could also use a low-side switching arrangement, where the switch is now located between the electrical load and the negative or low side of the source. In both scenarios, high or low-side switching, open switches interrupt current flow through the electrical load, and closed switches allow current flow through the electrical load. This being said, a low-side switching arrangement isn't exactly the safest switching arrangement for reasons I'll explain when we discuss circuit protection devices and ground, a handy reference point, and a major source of confusion for most people. Again, in both types of switching arrangements, a switch controls the fundamental on or off state of the electrical load simply by changing its resistance from one extreme to the next. Open switches present infinite resistance, closed switches present 0 ohms of resistance and allow current flow. In between these two extremes of 0 ohms and infinite ohms is where we find typical electrical loads like motors, lights, and components like resistors. In this spectrum from 0 ohms to infinite ohms, we could arbitrarily divide things into one of two classes. Conductors are devices with low resistance. Insulators are devices with high resistance. It'd be a terrible mistake to classify a conductor as something that conducts electricity, and an insulator is something that does not conduct electricity. I'm here to tell you that by that definition, everything is a conductor. Just like everything is flammable. Get something hot enough and it will burn. Give a charge enough incentive to move, i.e. extremely high voltage, and it will move through an insulator or even through an air gap in the form of a potentially dangerous arc. What do you think lightning is? Air, something with a high resistance, conducts electricity at extremely high voltages. Here's a clip of glass, ordinarily considered an insulator, conducting electricity at high voltages. Like I said, everything is a conductor. For now, let's just stick with our first definition. A conductor is a device with low resistance. An insulator is a device with high resistance. Some conductors conduct electricity better than others. Obviously, glass would not be my first choice when wiring up my house. Not only is glass not a good conductor, you'd break it every time you had to bend a wire. It is for this reason materials like copper and aluminum are used to form the conductive core of a wire. Not only are these metals better conductors than glass, they can handle the mechanical stress of installation or repeated deformation without breaking or becoming an open circuit through which no current can flow. This conductive core is then sheathed in insulating plastic, and you've got a very safe and very usable conduit for electricity. The measurable difference between conductors and insulators of different materials and dimensions is the quantity of resistance, where resistance is again measured using the units of ohms. A related quantity, conductance, sometimes abbreviated as G, don't ask me why, is 1 over resistance. Good conductors have low resistance and high conductance. Conversely, good insulators have high resistance and low conductance. Conductance used to be measured using the unit of mho, where 1 mho is 1 over 1 ohm. You note the symbol for mhos is an upside down ohm. I am not joking about this. Nowadays, conductance is measured using the units of Siemens, symbolized using a capital S, where 1 Siemen is still 1 over 1 ohm. I tend to restrict my thinking to solely the resistance aspect of a conductor, where resistance is the opposition to current flow. The question is, what properties define the resistance of an object? If current is the movement of charges through something, and resistance opposes charge movement, how might one limit charge flow? Remember, an electron, the moving charge, is just like a tiny light blue colored billiard ball. It's a particle that occupies space, just like a person trying to get into a building. How would you limit or control flow of people entering a building? I don't know about you, but you know what I'd do? I'd make the path as narrow as long, and as circuitous and obstacle-laden as an IKEA showroom. I'd turn out the lights, throw a bunch of Legos on the floor, and make everybody walk barefoot. What if we wanted to do the opposite and allow more flow? I'd probably do the opposite of everything I just did. If I wanted more flow through a passageway, I'd make the passageway as wide as possible, short as possible, and I'd make sure the path is as clean and well lit as a church parking lot on a Monday. If you think about it, the same type of properties influence resistance. The path length, the path width or cross-sectional area, and what that path is made out of. If I make the path long, I increase resistance. So I'm going to put it at the top of our resistance formula. If I make the path wide or I increase its cross-sectional area, I decrease resistance. So I'm going to put area at the bottom of the resistance formula. If I make a path out of a material that has an innate tendency to oppose charge movement, I increase resistance. So I'm going to put this property at the top of the resistance formula. This is the symbol for the innate resistivity of a substance. It's kind of a funny P-shaped thing called rho. The first two, length and area, are kind of no-brainers. If the length of a conductor increased and everything else was kept constant, the resistance should go up because there's more stuff to battle through. Conversely, if the length of a conductor decreased and everything else was kept constant, the resistance should go down because there's less stuff to battle through. It makes sense. Typically, length is measured in units of meters. If the cross-sectional area of a conductor is increased and everything else kept constant, the resistance should go down because there's more room for the charges to walk down the passageway side by side. Conversely, if the cross-sectional area of a conductor is decreased and everything else kept constant, the resistance should go up because there's less room for charges to walk side by side. Makes sense. Typically, cross-sectional area is measured in units of square meters. Regarding this third property, the innate resistivity of something, what are we supposed to make of this? Resistivity is simply a physical property of a material, similar to a boiling point or a relative permeability of something, meaning it just is what it is. Gold will have innate resistivity different than silver, and silver will have innate resistivity different than compressed cheese. The units of resistivity are all over the map depending on which corner of the internet you're frequenting, but I like using resistivity in terms of ohm meters for reasons we'll learn about later, as in 2 seconds later, as in right now. Do a unit check. Do our units make sense? If we're trying to find the resistance in units of ohms, what do you get if you take an ohm meter times a meter and divided it by a meter squared? The answer is an ohm. Oh my gosh, it worked. You should be slapping your head right now in sheer amazement because I just tricked you into doing math without realizing it. I know we didn't use any numbers at all, but we just derived the resistance formula just by thinking about it. Beyond directly calculating resistance, algebraic rearrangements of this same formula can be used to solve for individual properties. For example, if you wanted to solve for resistivity, given known resistance, known length, and known area, an algebraic rearrangement of the resistance formula demonstrates the resistivity is resistance times area divided by length. This algebraic permutation implies that if you are presented with an object of known resistance, known cross-sectional area, and known length, one could determine its resistivity, and by extension, its material composition. As an exercise to the viewer, I invite you to algebraically manipulate the resistance formula to solve for area, given known resistance, known resistivity, and known length. And again, to solve for length, given known resistance, known resistivity, and known cross-sectional area. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Area equals resistivity times length divided by resistance. Notice I started this manipulation by taking the inverse of both sides. Other algebraic methods should yield the same results using more or less steps. This permutation implies that if you're ever presented with an object of known resistance, known resistivity, and known length, one could easily determine its cross-sectional area. Length equals area times resistance divided by resistivity. This permutation implies that if you're ever presented with an object of known resistance, known resistivity, and known area, one could determine its length. Now that you've had some exposure to this formula and its various algebraic permutations, let's make use of it to directly calculate the resistance of an object. Really, the hardest part about this formula is getting everything in terms of the correct units. First off, you are never, ever going to find a conductor with a cross-sectional area in units of square meters, because common conductors like wires ordinarily have a small cross-sectional area, much less than a meter squared, permitting them to be flexible and routed through small spaces. This necessitates an understanding of engineering prefixes and an ability to seamlessly convert between these different levels. Let's try an illustrated example of the resistance formula. Consider an aluminum bus bar through which current must travel end to end. The bus bar has a width of 6 centimeters, a height of 2.5 centimeters, and is 2 meters long. Aluminum is known to have an innate resistivity of 2.65 times 10 to the negative 8 ohm meters. Without even touching the resistance formula, I can already tell you the resistance value we obtain is going to be extremely, extremely small. Because 1, aluminum is a good conductor, and the innate resistivity of aluminum is small. 2, the bus bar isn't really that long in comparison to a transmission line. And 3, it's got a pretty big cross-sectional area if you compare it with a typical wire. Do you see what's going on here? Every single property relevant to the resistance formula is working together to make this a low resistance path. It's made out of a highly conductive material, it's short, and has a relatively large cross-sectional area. That's the point. Bus bars are designed to be low resistance paths with the purpose of conducting a substantial amount of electricity with a minimal opposition and distributed to other circuits without losses. Right up front, I know my answer should be very small, and we should be prepared to use engineering prefixes to easily write and read this small value. Perhaps the hardest challenge we're faced with in using the resistance formula is to put everything in terms of the correct units. A centimeter isn't really an official engineering unit because it's stranded in the no man's land between a meter and a millimeter. While not an official engineering unit, centimeters are common dimensional units because they're on a scale easily understandable by humans. Given the resistance formula necessitates units of meters, perhaps the best approach is to convert everything into meters first. A centimeter is 1/100th of a meter, therefore 6 centimeters is equal to 0.06 meters, and 2.5 centimeters is equivalent to 0.025 meters. Now that we've got all our properties in the correct units, we need to determine the cross-sectional area. The cross-sectional area of a rectangle is width times height. 0.06 meters times 0.025 meters yields a cross-sectional area of 0.0015 or 1.5 times 10 to the negative third meters squared. Do not be tempted to apply engineering units to the cross-sectional area figure. Leave it exactly as it is in units of meters squared. Individuals employing scientific calculators using engineering format will be absolutely overjoyed that you cannot get this wrong because the calculator automatically accounts for engineering units. If you wanted to, you could also express these same dimensions as 60 millimeters and 25 millimeters. 60 millimeters times 25 millimeters still yields an area of 1.5 times 10 to the negative third meters squared. Again, do not be tempted to apply engineering units to the cross-sectional area figure. Leave it exactly as it is in units of meters squared. Now all we have to do is insert resistivity, length, and cross-sectional area into the resistance formula. 2.65 times 10 to the negative 8 ohm meters times 2 meters over 1.5 times 10 to the negative third meters squared yields a resistance of roughly 35.3 microohms. See, I told you it'd be small, as in 0.0000353 ohms. This is an extremely small opposition to current. Any electron that enters this bus bar is just going to cut through it like Anakin Skywalker at a Jedi preschool. That's the point. A bus bar's purpose is to be a low resistance conductor used to distribute a lot of current to other parts of a system without losses. Consider the following scenarios and think about how these modifications would affect the resistance of this bus bar. No calculations needed. Just think about it. Consider each scenario independently and simply determine whether you would expect resistance to increase, decrease, or remain the same. What if the bus bar was shorter? What if the bus bar was longer? What if the bus bar was wider? What if it was thinner? What if we made it out of gold, a material with markedly small innate resistivity? Finally, what if we made it out of rubber, a notoriously poor conductor with an extremely high innate resistivity? By all means, pause the lecture and think about this. Again, no calculations required. Does resistance go up, go down, or remain the same? If you're tracking, you should have arrived at the following conclusions. First, if the bus bar was shorter, there'd be less material to battle through, so chances are resistance would decrease. Conversely, if the bus bar were longer, there would be more material to battle through, so chances are resistance would increase. In summary, short paths have less resistance, and long paths have more resistance. Next, if the bus bar was wider, the cross-sectional area would increase, so chances are resistance would decrease. Conversely, if the bus bar was thinner, the cross-sectional area would decrease, so chances are resistance would increase. In summary, paths with larger cross-sectional areas have less resistance, and paths with smaller cross-sectional areas have more resistance. Finally, if the bus bar was made out of any other material with an innate resistivity less than aluminum, gold included, chances are resistance would decrease. Conversely, if the bus bar was made out of any other material with an innate resistivity more than aluminum, rubber included, chances are resistance would increase. In summary, paths made out of better conductors have less resistance, and paths made out of poorer conductors have more resistance. Hopefully, the influence of these properties on resistance should make sense. Moving on, let's talk about wires. Only in bizarro world do wires have rectangular cross-sectional areas and are commonly known to have circular cross-sectional areas. Resistance formula for a wire with a circular cross-sectional area remains unchanged. Resistance still equals the resistivity times the length divided by the cross-sectional area, only this time the cross-sectional area is circular rather than rectangular. The area of a circle can be calculated using one of two formulas, using either the radius, being a measurement from edge to center, or the diameter, being edge to edge passing through the center. Area equals pi r squared, or area equals pi over 4 times the diameter squared. Note the ratio pi over 4 precedes the multiplication of diameter squared. Consider a 20-meter long cable made out of copper with an innate resistivity of 1.68 times 10 to the negative 8 ohm meters with a 15 millimeter diameter. Let's determine the resistance of this cable. We first need to determine the cross-sectional area. The cross-sectional area of a circle is pi over 4 times the diameter squared. Pi over 4 times 15 millimeters squared yields a cross-sectional area of roughly 176.7 times 10 to the negative 6 meters squared. Again, do not be tempted to apply engineering units to the cross-sectional area figure. Leave it exactly as it is in units of meters squared. Now all we need to do is insert resistivity, length, and cross-sectional area into the resistance formula. 1.68 times 10 to the negative 8 ohm meters times 20 meters over 176.7 times 10 to the negative 6 meters squared yields a resistance of roughly 1.9 milliohms, which is a pretty respectably small resistance for a cable that stretches a length of 20 meters. Despite its length, it's relatively thick and it's made out of a highly conductive material, thus a small resistance. Now that we've seen the resistance formula demonstrated for both conductors with rectangular cross-sectional areas and circular cross-sectional areas, see if you can try these example problems on for size. Consider a 1.5 meter long bus bar made out of copper with an innate resistivity of 1.68 times 10 to the negative 8 ohm meters with a 5 centimeter width and a 2.7 centimeter height. Problem 2. Consider a 3 kilometer long cable made out of aluminum with an innate resistivity of 2.65 times 10 to the negative 8 ohm meters with an 8 millimeter diameter. See if you can determine the resistance of these two objects. Express your answer using the most appropriate engineering prefix rounded to the tenths place. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. Let's take a look at the copper bus bar first. 5 centimeters is equivalent to 0.05 meters or 50 millimeters. 2.7 centimeters is equivalent to 0.027 meters or 27 millimeters. If you're using a scientific calculator making use of engineering format, either figure will work. The cross-sectional area of a rectangle with a width of 0.05 meters and a height of 0.027 meters is 1.35 times 10 to the negative third meters squared. Now all we have to do is insert resistivity, length, and cross-sectional area into the resistance formula, which yields an extremely small resistance of roughly 18.7 micro-ohms. Let's do the same thing for the aluminum wire. 3 kilometers is equivalent to 3,000 meters. 8 millimeters is equivalent to 0.008 meters. The cross-sectional area of a circle is pi over 4 times diameter squared. Pi over 4 times 8 millimeters squared yields a cross-sectional area of roughly 50.3 times 10 to the negative 6 meters squared. Again, do not be tempted to apply engineering units to the cross-sectional area figure. Leave it exactly as it is in units of meters squared. Now all we have to do is insert resistivity, length, and cross-sectional area into the resistance formula, which yields a resistance of roughly 1.6 ohms, which is still pretty small given the cable stretches 3 kilometers. Hopefully this went well. If it didn't, by all means figure out where you went wrong and rectify that error because we are moving on. Very often students are mathematically capable yet have issues with rounding. If you're getting answers close to those illustrated but not exactly as illustrated, chances are you're rounding too early. Remember to round only the final answer. All work up until the final answer must include all figures. Scientific calculators with a previous answer key make it easy to reuse previous results rather than tediously re-entering them. Before we bring this lecture to a close, allow me to quickly introduce the American wire gauge and discuss how resistance formula is associated with the American wire gauge. I was going to package a discussion of the American wire gauge into another separate lecture. However, it's too easy and so directly related to the same topic, my hopes are the discussion will be brief and to the point. The American wire gauge is a standard used to designate wire size, where the gauge number of a particular wire is inversely proportional to the size. Smaller gauge number means bigger wire. Larger gauge number means smaller wire. This is something similar to the sizing system used by shotguns, a topic you may or may not be familiar with, whereby a gunsmith divides a pound of lead into equally sized balls that fit down a barrel. If a gunsmith takes a pound of lead and divides it into 20 smaller balls of lead, this is the size that fits down the barrel of a 20 gauge shotgun. If, however, the gunsmith takes that same pound of lead and divides it into 12 larger balls, this is the size that fits down the barrel of a 12 gauge shotgun. Get it? The 20 gauge is smaller than the 12 gauge because the same pound of lead has been divided more times. This is the same scheme used by the American wire gauge. The American wire gauge is a set of standardized sizes where the gauge number is indicative of how many times a wire is drawn through a die to obtain a wire of a specific size. Every time the wire is drawn through a die, the wire gets thinner. This is obviously an oversimplification, but it'll do us just fine for now. A 4-gauge wire is drawn through a die 4 times and has a diameter of 5.19 millimeters. If you draw that same wire through a die 10 more times, it gets thinner and thinner every time it's drawn through it, and it becomes a thinner 14-gauge wire with a diameter of 2.59 millimeters. Get it? Higher gauge means a thinner wire, or one with a smaller diameter. Given diameter is a property that directly influences cross-sectional area, think how gauge number influences resistance of wires of the same length. Consider the thicker 4-gauge wire versus the thinner 14-gauge wire. It should be obvious that a 14-gauge wire has more resistance than an equal length of 4-gauge wire because the 14-gauge wire has a less cross-sectional area than the 4-gauge wire. It makes sense. Other statistics are commonly available for wire size using the American wire gauge that make calculation of resistance stupidly simple. Here's one such table identifying the diameter in millimeter and resistance per 1,000 meters for specific gauges of wire of copper and aluminum composition. Additionally, notice the scale goes into the 0 or aught zone to accommodate super large wires. I should note that larger diameter wires aren't single solid cores, but are actually bundles of smaller wire strands. The fibrous nature of these strands allow bigger wires to be handled and bent easier. This being said, the data in the other columns accommodates for this difference in construction. Yes, one could painstakingly calculate the resistance of a given length of a wire of a specified diameter and composition using the resistance formula as previously, but one could also just easily look it up using this table. Let's say we wish to know the resistance of 200 meters of copper 12-gauge wire. It is a known fact that copper 12-gauge wire has a resistance of 5.2 ohms per 1,000 meters. We can use this fact to determine the resistance of our wire of interest using a process similar to unit conversion. 200 meters times 5.2 ohms per 1,000 meters, units of meters cancel out, demonstrates this length of wire as a resistance of approximately 1 ohm. See if you can use this wire table to determine the properties of interest for these example problems. Determine the resistance of 600 meters of 18-gauge aluminum wire. Next, determine the length of a copper 6-gauge wire that is known to have a resistance of 2 ohms. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Given aluminum 18-gauge wire has a resistance of 32 ohms per 1,000 meters, 600 meters of 18-gauge aluminum wire has a resistance of roughly 19.2 ohms. Finally, given copper 6-gauge wire has a resistance of 1.3 ohms per 1,000 meters, a length of 6-gauge wire having a resistance of 2 ohms must therefore be roughly 1,538.6 meters in length. Again, think of these table entries as a means of unit conversion. Arrange the conversion factor such that the unit you want is on the top and the unit you don't want is on the bottom. The units you don't want cancel out and you're left with the units you do want. Alright, that's about it for this lecture. In conclusion, this lecture presented the concept of resistance and opposition to current flow. We introduced the switch, an electromechanical device that changes resistance from infinite to 0 ohms to stop or start current flow. We discussed the basic differences between conductors and insulators. We We discussed the properties that influence resistance of a conductor, length, cross-sectional area, and material composition, and determine the relationship between these properties to calculate resistance in units of ohms. And finally, we introduced the American wire gauge sizing system and learned how to use a wire table. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.